Hello, my name is Ian. I'm one of the summer interns here at Tyndall and IPIC, and I took part in the Heterogeneous Integration Theme workshop. This is my laser presentation. It's just on the topic of how does a laser work. It explores it on a very basic level. I tried to make it so that anybody could understand what's being presented here. It's mostly a PowerPoint presentation, but we also have a few animations in there, so hopefully you don't get too bored. Please enjoy. Let's start by taking a look at some applications of lasers, which you might see in your day-to-day life. When you think of a laser, you might be like me and immediately have this image of a laser pointer spring to mind. But of course, there are other applications. In the medical space, we have laser eye surgery. You may have a laser printer at home, which you use to print documents for work or just whatever. And of course, in the manufacturing industry, there are things like laser cutting and engraving, which you might use to engrave a pattern or a design onto a material. So those are some applications, and you can see that it's used almost everywhere. But you might not know what actually is a laser. Well, a good place to start is actually to look at the name itself, laser, because laser is actually an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. And that might not mean all that much to you at the moment, but it's a very good point from which we can start looking at how lasers work. To get an understanding of how lasers work, we're going to go right down to the atomic level. What I have here is a model of an atom, a pretty simple one at that. It consists of a nucleus in the center. We have an electron, which orbits around it and can occupy one of either a ground state or a first excited state. It's not the most accurate model, but I think it will do for the purposes of this explanation. An important thing to note about these two energy levels is that there is a constant energy difference between them. Why this is important to us is because if somehow our electron, which by default we have as resting in the lower energy level, if that electron somehow gains energy, which is equal to this energy difference, it will jump from the ground state to the excited state. One way for the electron to gain this energy is for it to absorb a photon, which is a particle of light, a particle of electromagnetic radiation. If the energy of this photon is exactly equal to the difference in energy between the two energy levels, the electron will transition like so. However, an electron in its excited state will be less stable than when it was in the lower ground state. As a result, it will eventually transition back down, releasing a photon as it goes, and this photon will have energy equal to the energy difference. So in other words, there is a radiation of a photon. This phenomenon is called spontaneous emission. It's not the same as stimulated emission, but the two are closely related, as we'll see now. Here we have three atoms. Two of them are in an excited state, the other isn't. The first one emits this spontaneous photon, and interestingly, this photon can actually cause the unstable electrons to transition back down into the lower energy level, which itself will release another photon, as shown. As we can see, the first photon has stimulated the emission of the other two photons. Interestingly, due to the quantum mechanical properties of photons, the two stimulated photons will be almost identical to the original one. They'll have the same energy because the difference in energy is the same in all three atoms, but they'll also have the same direction and orientation. We say that the photons emitted by stimulated emission are coherent, and this coherence gives rise to the characteristic properties of laser beams. For example, laser beams are usually quite bright. That's because they have a very high intensity, which results from the way that the photons interact with each other. Their energies are additive, which leads to a very high brightness. Laser beams are also collimated, meaning that the laser waves very rarely diverge from the path that they're traveling along, and if they do diverge, it's very little. This is because all of the photons that are emitted have a pretty exact trajectory. Another characteristic of laser light is that it is monochromatic, so it only has one color. This is because the color depends on the wavelength of the light, and the wavelength in turn depends on the energy of the photons that are emitted. This dependence is given by the formula E is equal to hc over lambda, where lambda is the wavelength and E is the energy. Remember that the photons emitted are almost always equal in energy, or and if they're not equal, they'll be very close. So as a result, the wavelengths are almost all the same, and then therefore the color is almost uniform. Now that we have a basic idea of how a laser works, I just want to take a quick look at a common way of making a laser, which is using a Fabry-Perot laser cavity. So this consists of an active region surrounded by some semiconductor cladding layers, and just note that the edges are reflective. If we attach a power source to this system, such as a battery, there will be a current flow which will cause spontaneous emission to happen in the active region, and therefore there will be stimulated emission, so we'll end up with a load of photons in the active region. These photons will all be traveling in the same direction, however they will reflect off of the reflective edges and stay in this region for quite a while, causing even more emission. So we get quite a lot of photons and therefore very high intensity and high brightness light in this region. I am going a bit over time here, so I'll end it there. Thanks very much for your time.